that brief delay. Thanks everyone for coming. As I said, Ron and I are going to tag team this, so I'm going to start with a little bit of just the basic information, make sure everybody's up to speed. For some of you, this should be more than a review. For others, it might be new information. And the way we want to try to handle this session as well, feel free, if we're talking and you're not sure what we're saying, by all means, definitely raise your hand and let us know. And we also have enough time built into breaks that if you have a very detailed question and you're not sure you want to answer it, or sorry, have it answered at this point in time, find one of us during the break and we can have a long discussion about your passion for vibration. Okay, so vibration basics. Again, vibration, when we're talking about that, it's an oscillatory motion about some fixed point that can travel through a mechanical structure, right? So when we're talking about the human body, any part of your human body that's in contact with a vibrating surface has the ability to have that vibration be transmitted through that body. So when we're thinking about vehicles such as the forklift here, we have different types of vibration. So the hands in contact with the steering wheel can get what's called hand-arm vibration. When we're thinking about the feet, feet are sort of an interest to me, and if anyone else wants to have this discussion again later on, we can get into it at the break. But we have to also consider that the foot can be a contact point for vibration and can also have challenges in terms of some of the health effects we're going to be talking about. So in this case here with the forklift operator, the feet are in contact with the pedals, which can transmit vibration to the body. And where most of us are familiar when we talk about whole body, it's the interface between the seat and the backrest of the seat, and transmits vibration to the individual. Up where I'm from in Sudbury, when we think about a mining context, we have lots of folks using these drills. These drills produce vibration, and so we've got high rates of hand-arm vibration syndrome amongst many of these mine operators. And we're now seeing issues of vibration through the platform. So these drills are attached to the platform. They will cause vibration to be transmitted into the feet, and in some cases we're getting what's now being termed vibration-induced white feet. So when you're measuring vibration, some of the factors that are key. So basically when we're talking about what a magnitude is, we're really talking about the concept of amplitude. So a good way of thinking about it, and Marty, I think you're the first one that did this as one of my grad students years back. If you're driving over a real rough road and you hit a pothole and you feel like you're going to sort of bounce off your seat, that gives you an idea of the magnitude or the amplitude of that vibration potentially. So we'll measure that typically in meters per second squared. Frequency then has to do with the number of bounces, if you like, per second. It's measured in hertz. And why frequency is important is when we talk about resonance. So each body structure has a particular frequency that they are going to be maximally amplified at. And I'm going to get to that in a second. The other factors that are important is it's really critical that the direction of vibration is reported. So it's typically measured in X, Y, and Z direction. So here you can see a picture here that indicates Z is vertical when we're talking about exposure at the seat, X is moving forward, and Y is side to side. So it's important that you report which axis you're doing your measurement from, and then duration of measurement is also critical. So we need to know how long that vibration signal was sampled for. Okay? So here's that concept of resonance that I was talking about. So the idea behind resonance is certain parts of our body are affected by different frequencies of vibration. And this is going to be important when Ron and others talk about health effects. So what we know from that is if an individual, for example, is exposed to, let's say, a lower frequency, particularly around 3 to 5 hertz, that's going to be more likely linked with adverse health effects in the pelvis and the spine region. But it's the higher frequencies that are more problematic when we talk about the hand-arm system, so 30 to 50 hertz, and when you get up into the fingers, even higher. The toes and feet, there's still some discrepancy about what are the exposures that are important, but from some of the research we're currently doing, it looks like they're more similar to the hand-arm finger system, so 40 to 50 hertz around for the actual foot, and the toes are responding to higher frequencies as well. So we need to keep in mind that the frequency is important. Now, just sort of in this room here, what types of industries, tools, or equipment can expose workers? So we'll just do it by a show of hands. How many folks are involved with construction or concerned about sort of construction vehicles? Okay, so scrapers, maybe loaders, dozers. Okay, anyone interested in lift trucks, forklifts, working in warehouses? Okay, good. What about if we look at some of the hand arm using drills, jackhammers, impact drills, scalers. So lots of hand-arm folks too. So we've got the right people in the room, and we'll be able to talk through some of those particular pieces of equipment. One good source of information, if you haven't been there before, the European Union is in reality, they're further ahead than we are in North America with addressing vibration issues. And they've put out some good information that's really easy and practical to use. So it's called the EU Good Practice Guide to Whole Body Vibration, and I've got the link later. But what they've done is they've reviewed a lot of literature and a lot of databases that are out there, and they've put together these summary tables. So what they've got is the acceleration or the magnitude of exposure up here, and pictures of the vehicle types, and they've given you the ranges from this zone here in yellow is the 25th to the 75th percentile. So it gives you an idea of the range of exposures that have been reported. Just as an indication, you can see there's some types of equipment that there's a very large range of publicly available data, but the magnitudes, for example, for this paver go from 0.6 meters per second all the way up to over 1.8. So again, to be able to interpret that, we're going to be talking later on about what type of information is important for you to have in a report, so you'll know whether you can really compare the measurements that you've done to other measures that have been published. So some other vehicles that exist. And they've done the same thing for hand-arm vibration. So, oops, I don't know what I did, Richard. Did I press a button that I shouldn't have? Whoa, tricky. Thanks, that's exciting. Okay, I'm going to stop playing with the computer screen. Obviously, I'll make some problems. But they've published the same thing for hand-arm vibration. So again, the EU Good Practice Guide to Hand-Arm Vibration, if you Google that, it's a PDF document that you can download. And within that, they've got examples of data that exists for a lot of equipment that will expose you to hand-arm. So from chainsaws to needle scalers, etc. I'm not going to really talk about foot-transmitted vibration today. Probably for where I am, it's not as relevant. But if any of you are having issues where people are standing on vibration surfaces, so crushers or working on platforms where they're drilling off of, come talk to me at lunch and we'll have a nice discussion. So Dr. House, myself, and a colleague, Aaron Thompson, published one of the first papers that talked about this as a clinical issue where an individual who was exposed to foot-transmitted vibration was diagnosed with vibration whitefoot, and that was independent of hand-arm vibration exposure. So some of the factors that are really important that we need to think about, the magnitude of vibration gives us an indication of sort of that bounce height again. We need to always recommend or report the direction of our measurement. Frequency is really critical. We have to think about all the points of the body that are in contact and can potentially be transmitting vibration. How long is an individual exposed to that? So are we talking an hour per shift, or are we talking 7 hours per an 8-hour shift? And then other factors that we'll talk about a little bit later on. So the worker's posture becomes important. Things like grip strength when we're talking about hand-arm vibration. The mass of both the vehicle, if we're talking whole body, and also the individual. These are all factors that need to be considered. So that was just a real quick overview of basic information. I'm now going to pass it off to Dr. House, and he's going to talk about some of the health effects. You can. I just like the arrows, but you can use this too if you want. That's forward? Yeah.
Okay. Okay, that's great. Thanks very much. Good morning, everyone. It's great to see everybody here. So obviously there's more interest in vibration than I thought. So I've been feeling like a voice in the wilderness, assessing people for halves for so many years. So I'll just briefly go over health effects. This isn't the focus of this conference, but this workshop, but I think we should cover the health effects so we know the harm caused by the exposures. So my experience comes from working at the Occupational Health Clinic at St. Michael's Hospital. We started this clinic in 1991. Peter Palmier, who was an international expert in hand-arm vibration, he was the person who opened our clinic, and he was my mentor, so I owe a lot to Peter. And now we assess over 200 people for halves every year. The number fluctuates from year to year, but it's about 200. And this is by far the largest center for the clinical assessment of workers for halves in Canada. So I'm supported in what I do by CREOD. We've already talked about CREOD for the research arm of what I do, but also the Occupational Disease Specialty Program, which is a program we've developed at St. Michael's Hospital with the compensation board, and that provides workers referred to us for in-depth assessment. So that combination of the large volume of clinical workers that we see for in-depth assessment and CREOD for the research arm has helped me considerably in the work I do. So I'll just work through the health effects quite quickly for whole body vibration, and then talk about hand-arm vibration. So for whole body vibration, we can think of acute effects and chronic effects. For acute effects, there can be discomfort. For example, you can develop muscle aches and pains. You can develop nausea and feel vague discomfort from the exposure. With ongoing or higher exposure, you can develop muscle fatigue and decreased proficiency for carrying out a particular task. So that can affect your ability to actually carry out the work. There can be physiological changes like increase in heart rate, respiratory rate, cardiac output, and other physiologic effects. So in terms of chronic effects, the main one is back disorders, and that's been recognized for a long time. NIOSH first suggested this back in the 70s. When they looked at this evidence in 1997 in that large document they produced for musculoskeletal disorders and looking at various risk factors, they felt there was strong evidence that vibration white finger causes back disorders. There have been a number of meta-analyses since then, and the one that really led the way was by Bovenzi and Hulshot, which showed that, looking at a number of published studies and carrying out a meta-analysis, that whole body vibration exposure was associated with back pain, degenerative changes in the spine, and also intervertebral lumbar disc disorders. And there have been other meta-analyses since then. So the evidence is strong that whole body vibration causes a number of disorders of the spine. So hand-arm vibration is more complex in terms of the health effects, and most of the clinical work I do focuses on that, and there are the various components, the vascular, sensory, neuromusculoskeletal. So just quickly going through these, the vascular effects, these are the effects that are best documented, and the main one is this Raynaud's phenomenon in the hands, which refers to the fingers turning white in the cold. The damage is done by the vibration, but after that damage, the cold stimulus causes the blanching. Some workers say that the vibration itself will cause blanching. So again, NIOSH has looked at the evidence for this in that 1997 document. They felt there was strong evidence that Raynaud's is caused by hand-arm vibration, and the risk of developing Raynaud's phenomenon is related to the intensity and the duration of exposure. And we often talk about occupational diseases taking a long time to develop, but if the intensity is high, the latency can be quite short, even less than 2 years for this vascular component of halves. So this is a common exposure, and a lot of people can get this health effect, and they can get it fairly fast. So this is, just on the left, I showed you a photo of Peter Palmier. He was my mentor, and equally I've passed this along to Aaron Thompson, who was a graduate of our residency program at the U of T. It's like a medieval guild association, you know, from Peter to me and on to Aaron. I'm very happy that Aaron has shown an interest in this. And you can see the hands of a worker that we saw in the clinic. He doesn't walk around with hands like that. We were testing him. We put his hands in cold water, thermometry, and then measured his finger temperature. But the cold water stimulus, which I believe at that time was 10 degrees centigrade for 5 minutes. After that cold stimulus, which isn't that cold, he was walking around with hands like that for most of the morning. And then you can get very serious changes in the fingertips because of decreased blood supply. You can get ulceration of the fingers, and these areas can get secondarily infected, and you can lose digits because of that. You can develop gangrene of the fingers. And we still see people who have lost digits because of this. This isn't something that happened many years ago and is gone. we're still seeing people with these injuries, especially in the mining sector and in the construction sector. So in the TLV booklet for HandArm Vibration, the ACGIH TLV booklet, it mentions the Stockholm classification, so I'm just putting that up for interest. There's a classification for the vascular component of HAVS and also the sensory neural. The vascular component is based on the frequency of blanching of the fingers and the extent of blanching, and also whether you get those trophic changes that I just showed you in the most severe stage. The sensory neural component is based on the nerve damage and the symptoms of numbness and tingling and abnormalities that you pick up in the examination of workers, the neurologic exam. So neurologic abnormalities, we see two different types. I guess is there a pointer on this thing? I'm afraid to touch this. Anyway, so we see effects on the fingers, the distal fingers. The nerves can be damaged, and you can get a digital neuropathy, a digital sensory neuropathy. And that's the damage that is considered part of HAVS. But also, we see a lot of people who develop neuropathies around the wrist area, compressive neuropathies of the median nerve with carpal tunnel syndrome or the ulnar nerve. So we see these two different kinds of problems. But HAVS includes the Raynaud's and the digital sensory neuropathy. It doesn't include the carpal tunnel and the ulnar neuropathy. It also includes musculoskeletal effects. But there's more and more evidence that carpal tunnel syndrome is also caused by vibration exposure, because the higher frequencies of vibration are absorbed by the fingers, the vibration frequencies above about 100 hertz, but the lower frequencies are transmitted into the wrist and up into the forearm and elbow and shoulder. And there's increasing evidence that HandArm vibration exposure also is associated with the development of carpal tunnel syndrome. The problem is that people also have a lot of ergonomic stressors from holding and manipulating the tools, a lot of flexion and extension at the wrist, and it's hard to sort out the relative contribution of the ergonomic factors in vibration. So the ergonomic factors are stronger risk factors, but after accounting for them, there's also evidence that vibration may contribute to these compressive neuropathies at the wrist. And so you can see, again, NIOSH did their review in 1997 and said there was evidence, but not strong evidence, of vibration causing carpal tunnel syndrome. And then another review by Palmer, about 10 years later, used very similar wording. Reasonable evidence for a twofold increase for vibration, but greater evidence for the ergonomic stressors. And then the musculoskeletal component, it's not as clearly defined as the vascular component and the sensory neural. And again, because of this problem of confounding with ergonomic factors. But in Ontario, the compensation board uses grip strength, and there's evidence from epidemiologic studies that HandArm vibration decreases grip strength, and also evidence from histologic studies of direct damage to muscle, the Necking et al. Paper. And that just shows some of the damage. It's a little hard to, it's actually, these, well, in here, these muscle fibers in here have shrunk, and the staining is a bit different. And so there's actual histologic damage from to muscle from the vibration. So that's a very quick overview of health effects. And I just want to talk a little bit about the reporting and recognition of HAVS in Canada, because this is a problem. We don't have any legislative requirements for health surveillance. I think a few companies may do this, some of the mining companies, but not many. But most people who are exposed in Canada and Ontario have no surveillance to see if they've picked up damage from vibration. And we're really constrained to use compensation board data. So we looked at this compensation data in Canada over a 6-year period from 2003 to 2006. So I did this with Aaron Thompson, who was I think he was doing a clinical fellowship with us at that time, Elise Turcot from Quebec, and Sammy Yoakum from BC. And you can see the number of accepted claims from the various provinces. that 940 from Ontario really stands out, and that's largely from our work at St. Mike's, but also there's a lot of assessment is done in the Sudbury area. And then once you move past Ontario, 187 claims from Quebec, 39 from British Columbia, just under 1,200 Canada-wide over a 6-year period. So we're averaging less than 200 accepted claims per year in the country as a whole. So you would think this is not much of a problem. And actually there was a famous review done of halves in the US by a fellow called Pecora around 1960. And he looked at compensation data from some large companies and couldn't find any evidence of halves. And he wrote a report saying basically halves had gone away, didn't exist anymore, somehow it had just disappeared. But it's just because we didn't have any good data to indicate there was a problem. And if you look at the number of cases expected, they're very high. So we estimated the number of cases expected in Canada from US data and also from British data. And you can see the estimates very high, 75 to 144,000. And we're only picking up a few hundred a year. So there's tremendous under-recognition or under-reporting of this. And this is a problem because HAVS is a sentinel health event of occupation. That means if you pick it up, if it's occurring, there's a problem in the company and something has to be done about it. And so we're missing this opportunity to do something and to rectify the exposures. And so in that sense, the clinical community has let everyone down. St. Mike's, we're doing these assessments, but we're a bit of a voice in the wilderness about this. And then if you look at legislation in Canada, well, in Ontario, we have no regulations for whole body or hand-arm vibration. When we looked at other provinces, a couple referenced the ACGIH TLVs in legislation. British Columbia and New Brunswick do, but I'm not sure about the enforcement of that. I don't think there's a great deal of enforcement. So there's a lack of legislation to address some of these key hazards in Canadian workplaces. And then if you look at other countries, the EU is well ahead of us. They developed an EU directive in 2002, which led to regulation in EU countries, including the UK. And that included an exposure limit value. So, for example, for hand-arm vibration, that's 5 meters per second squared as an A8 integrated value over an 8-hour workday. And also a daily exposure action value, which is 2.5 meters per second as an A8 integrated over an 8-hour day. And at that, if the exposure action value is exceeded, the company is required to take action and develop a control program, train people, and also do surveillance. In the US, the American National Standards Institute has developed a standard based on the EU directive, but there's no OSHA regulation. So the EU countries are well ahead of us in this regard. Okay, so I'll pass it back to Tammy. One more slide.
Okay. There we go.
Yeah, I just wanted I wanted to summarize everything. So I just wanted to make my key points, looking at the clinical manifestations, compensation data, and legislation. A lot of people are exposed to these hazards, both whole body and hand arm. The health effects are common. I mentioned with hand arm vibration with high intensity, you can get health effects within a couple of years. There's tremendous underreporting and under-recognition of these clinical conditions. A lack of legislation for vibration in Canada, so a lack of awareness of the hazards, and that's why we're here today, improved focus on prevention.
All right, so it's back to me for the tag team effort. So I'm going to review very briefly here some of the vibration assessment standards, and with a focus on the two that we're going to talk about after the break when we do our workshops. And again, by no means is this going to be exhaustive. If we wanted to learn the details of every single standard, we'd probably have to be here for at least a week, and I'm not sure most of you would want to listen to us for a full week. So we're going to give a real quick overview, and then there'll be time at the break. So in terms of whole body, probably the most sort of common or recognized standard would be ISO 2631-1. It'll be the one that we're going to talk about again later on this afternoon. 2631-5, it's a fairly new standard. It deals more with health effects when we're talking about exposure or risk to the spine in particular. I'm not going to talk about it, but if you do want more information on it, find me during the break and we can have a nice conversation. I'll mention the EU directives, but we'll focus on ISO. From a hand-arm perspective, again, ISO 5349-1. There's a -2 that gives you more information about how to actually apply and do what it says in -1. We're going to be talking about that standard. Again, I'll refer to the EU directives briefly. And ACGIH, the TLVs exist, but we're not going to talk about those today specifically. Real, I guess, basic information. And go through the airport with this sort of thing, you get strange looks all the time. A couple of my former grad students are back there, so as an aside, when we take this equipment underground, it sometimes gets exposed to explosive powder when they're blasting. And let's just say once or twice I've showed up at the airport with my gadgets and some residue. It didn't go well. So we now clean our equipment very thoroughly after having it underground. Okay, so there's lots of different equipment that exists for measuring whole body vibration, but the short and sweet of it is you need to have a triaxial accelerometer. And there's different sizes that these things come in, but this gives you an idea of what a common triaxial accelerometer will look like. I'm going to leave the accelerometers up here. People can come and look at them during the break, just because if they drop or you don't want to break them. But what we do with that accelerometer is it gets placed. There's a little hole in here, and I'm going to pass this around inside this rubber seat pad, and this is what the individual actually sit on. So I'm going to pass these seat pads around. You'll see that they're quite comfortable. We'll have people sit on them for 8 hours, and they don't really have any challenges with that. And then what happens is that all gets plugged into some type of a data logger. And there's different sizes of these things that exist. But the reality is it's a very sort of contained piece of equipment. So you've got your triaxial accelerometer, a seat pad, a data logger. We tuck this away, safely secure everything in the vehicle, and we record for usually minimally an hour, but some cases we'll record for up to 4 or 5 hours. We could record for a whole 8-hour shift if we were interested in doing that. So ISO 2631 is the typical standard for whole body vibration assessment. We're now going to have a math lesson. I'm going to go through all this in detail. Okay, don't worry, I won't, I promise. Oh, look, I did that again. Yeah, I'm trying to move my little, there we go. Okay, but this information will give you an indication of the steps that have to happen. So in reality, you move from taking your triaxial measurement, you have to apply frequency weightings. So it's prescriptive in ISO in terms of what those frequency weightings will be. So x-axis and y-axis are WD, WK weighting for Z. Then there's scaling factors applied for health, and from there you come down and you'll calculate what's called a frequency-weighted root mean squared acceleration. Crest factors are important. I'll talk about those a little bit later on, but if your crest factor is above 9, it means you also have to calculate a vibration dose value. And all of these things then are compared. This is what the weighting curves look like. And if we come down, those are compared to what's called a health guidance caution zone. This is just sort of a snippet to get you warmed up, and we're going to review it in step by step when we do the workshop. So I'm just kind of introducing the topic here. What the standard tells us is really between 4 to 8 hours is the most confidence. Those folks that have developed the standard say if you have a 4 to 8 hour duration measurement, or if you're comparing your A8 value, which is your 8-hour equivalent frequency-weighted acceleration to the standard, they're pretty confident that you're going to get a good prediction or a good indication of probable health risks. Okay, so what those values are, and this is in your laminated handout as well. So if you are exposed to an 8-hour equivalent or an A8 value, which is your 8-hour equivalent frequency-weighted RMS acceleration of less than 0.45 meters per second squared, your probability of health risks are quite low. Okay, so the language for the standard is there. However, if you're exposed to vibration above 0.9, it says above the zone, health risks are likely. So there's a high probability that the worker exposed at that level will be at greater risk for things that Ron talked about, like low back pain, degenerative problems, gastrointestinal tract issues. And then the equivalent vibration dose values are there. And I'll explain what a VDV is versus an A8 value when we do the workshop component. Okay? Oh, apparently I put it in here, but I'll come back to that later on this afternoon. So what I did then is I just put this in sort of a summary chart. The EU values are in white. You can't really see them, and that's because we're not really going to talk about them today. But as a summary, I wanted you to see that they're similar but a little bit different. So within the EU directive, the criterion values for health effects are slightly higher than what is published in the 2631-1, but it's based on the same measures and the same concepts. Okay. Now, from a hand-arm perspective, we're talking about ISO 5349-1, and again, you would use a triaxial accelerometer. So could use something again like this to measure for hand-arm vibration. And there's different ways that would get attached to a tool. I think our next talk is going to go through some of the specifics for hand-arm vibration measurement, so I won't cover it now, but if it's not covered, I'll talk about it in the workshop. The key is that this uses a WH weighting factor, so to calculate your frequency-weighted acceleration. Typically, hand-arm is sampled at a higher frequency, so 5,000 hertz. Whole body will often be sampled at 500 hertz. And what you're seeing then is one value. So you're looking to compare your 8-hour exposure to this criterion. So is your A8 HV value less than 2 meters per second squared? And if it is, then the ISO standard will tell us that your symptoms are rare for your vibration total value less than 2 meters per second squared. And as Ron said, it's a little bit higher for the EU directive. Gives you your action value of 2.5 and your exposure limit value of 5 meters per second. Okay, so it gives you an idea of how those compare to each other. There's a lot of controversy about the weighting curves for ISO 5349-1. I won't get into it here other than to suggest that the scientific community is not satisfied with this weighting curve. And there's a lot of discussion happening right now at the ISO Standards Committee about replacing this curve, but there's disagreement on what type of curve to replace it with. And the reason I say this, remember when we talked about resonant frequency? Well, if you look on the axis here at the bottom, I'm not going to touch the mouse because I don't want the screen to go crazy, but if you see where it peaks is at 16. So what this means is this weighting factor, in a sense, treats 16 hertz as the most potential damage to the hand-arm system. When in reality, we know from the work that Ron's done as well, it's the 30, 40 plus hertz, and in the fingers in particular, the higher frequencies, upwards of hundreds to thousands of hertz. And what you can see is that this curve actually downweights those samples. So the reason I think it's important is if you have somebody exposed to vibration and they get a HV value above 2 meters per second squared, chances are that they could be exposed to a much higher magnitude of vibration. This standard actually downweights the frequencies that we know to be most harmful to the hand-arm system. So therefore, there's, again, lots of work being done to try to figure out which is a better weighting curve. In terms of measuring it, Again, you have to have measurement in the X, Y, and Z axis, and we'll talk about how the AHV value is calculated again a little bit later, but the difference here is you are taking the sum of those axes and you take the square root of both your X, Y, and Z. So in whole body, you're making your measurement based on the axis that's most dominant, whereas with hand arm, you're taking the sum of all the axes, okay? So again, that was just to kind of whet your appetite to it. We're going to come back to some of those details when we do our workshops. So to kind of recap, it's just kind of reminding us again that vibration is really important. We know from the health effects that Ron covered. We know that any part of your body that's in contact with a vibrating surface has the potential to transmit that and has the potential to have some negative health effects. And in order to make some determination on risk, we do have to make comparisons to the criterion values that exist. And there are a number of standards, but today we'll focus on the ISO 2631 for whole body and 5349-1 for hand arm. Okay? And I think Ron's going to come back up and introduce our next speaker.